Hello and welcome back to the Advanced Malware Analysis course. This is the Initial Stages chapter, and in this part of the Initial Stages chapter we're going to be looking at first stage loaders. So let's just jump into it. So first we're going to go over the typical malware infection sequence. So first off we've got the initial stager, also known as the first loader, and these are typically Word documents, PDF documents, spreadsheets, and they can contain malicious macros, or they could contain some exploit that could exploit a specific vulnerability, such as the equation editor vulnerability. Next up we've got the loader, also known as the second loader. This is present in some samples. The Word document might just download the final payload, or it might download the second loader. So in this case the second loader is usually in the format of an executable, and this executable will reach out to a command and control server and download a final payload. And once again, this is normally in the form of an executable. So this final payload can then go ahead and reach out to the same command and control server, or potentially different ones, and download additional plugins that are either in the form of DLLs or executables. So this is just one of the more common methods that we see. So we normally see infection starting with a Word document, normally from malspam. That will then reach out to a command and control server, or perhaps it will have an executable embedded inside of it. So the macro will then go ahead and decrypt the executable inside of it, or download it from a command and control server. This loader executable will then go ahead and download the final payload from a command and control server, or it will be embedded inside of it. So in the case of ISFB, I believe they start off with a Word document. It will then download the first ISFB executable. That executable will have the next ISFB executable embedded inside of it. I believe it's compressed with APlib compression. And then once that decompressed executable runs, it will download the next payload, which will be injected into explorer.exe. And that is the main payload in the infection chain. So sometimes there's two loaders, sometimes there's one, sometimes there's three. It all depends on which group you're dealing with. But this is another method of potential threat intel, where you can gather information on how they like to infect machines. So one group using the specific malware family may use one loader, another might use two, and so on. So moving on from here, let's have a look at initial stages. So initial stages are usually received via spam campaigns, targeted attacks, exploit kits, and many other different forms of spreading. And they're typically in the form of Word documents, PDFs, Excel spreadsheets. Sometimes previously installed malware can act as first stage loaders for other families. So you may have an infection of Emotet, which will then download TrickBot, which will then download Ryuk ransomware, and so on. So that's actually quite common. Threat actors will often sell spots in their infection chain, so you can pay the Emotet group a certain amount of money to basically distribute your malware for you, which is normally a lot more efficient than having spam campaigns, because while a lot of people nowadays still open up spam emails and get infected, if you have malware on a system already, then chances are antivirus isn't going to be detecting your payload, and so you can keep everything in memory. There's nothing touching the disk, and it's just a bit more effective. So as you can see in the screenshot from the malware traffic analysis blog, you can see that IcedID is actually going ahead and downloading TrickBot onto the infected machine. And once again, this is another good indicator that you can use for threat intelligence. You can see which groups are collaborating with each other, and that's extremely helpful when you're creating links between the groups. So we'll be focusing on malicious Word documents in this part of the chapter, as they're probably one of the most common ones found out there. As I said, they're commonly used by many malware families, and the obfuscation is typically unique for each sample that you encounter, even if they're from the same malware family. They're also not just macro-based threats, as Word has been exploited in the past. So one of the most common exploits for it is the equation editor exploit, and there are also several possible methods of analyzing them, as well as being a fairly simple starting point when it comes to reverse engineering and malware analysis. So as you can see here, this is the equation editor exploit shown in AnyRun, which is a great sandbox software. So as you can see, Microsoft Word is started up, equation editor all of a sudden starts executing, which will then go ahead and download a file called unio.exe, which obviously, as you can probably guess, isn't the normal behavior of equation editor. So let's have a look at the potential pathways that malicious Word documents can take when it comes to infection. So start off with, we've got a malicious Word document. Now one pathway it can take is by using a highly obfuscated macro, which is executed by the auto open function. So that basically will execute the macro when the file is opened. You can also have a auto close function as well, which basically means it will execute when you close the document. That's quite effective because a lot of users think that, okay, well, if I accidentally enable the macro, you can close it out so it won't run or something, but that's not actually the case. It will execute on close rather than on open. So from this highly obfuscated macro, it will decrypt and extract a PowerShell script, which will then be executed, and that is responsible for downloading the next stage or potentially extracting it from its own source code. So this VBS to PowerShell script is very common. In fact, it's probably one of the most common methods you'll see. So that's one pathway, and the other pathway is through exploiting a vulnerability. And in this case, we're going to be focusing on the equation editor vulnerability, which is one of the most common vulnerabilities exploited in Word. You'll see it being used by groups spreading Lokibot and Agent Tesla and all those sort of things, because there's a load of software and tools out there that will auto-exploit equation editor for you. So you just have to select a payload and it will automatically put in shellcode that will exploit the vulnerability. So you don't need to worry about anything, it's just plug and play. So this exploit is triggered upon opening the document. I don't believe there's anything that requires you to enable macros or anything, so it's quite silent. So from there it will download or extract shellcode and execute that. And this shellcode will then typically download the next stage of malware from a command and control server. So this exploit is usually a buffer or stack overflow, and what occurs depends on the buffer size. So if there's a large buffer size that can be used, the executable may be stored in memory. Otherwise, it will most likely download it from a command and control server. So that's enough with the theory. Let's have a look at deobfuscating our first macro-infected Word document. So for the macro deobfuscation part, we're going to be looking at two different documents with macros inside of it that use different obfuscation. So the first one is an ersniff Word document, and the second one is a zloader XL document. So to start off with, we're going to have a look at the ersniff document. So let's extract that. Password is infected. And I have Process Hacker open just in case something gets executed and we have to quickly suspend it. So let's go ahead and double click to run. Open up Process Hacker. Okay, doesn't look like the macros have executed, so they have been blocked. That's good. So in that case, what we can go ahead and do, let's go to View, Macros, View Macros, and we're going to first look for an auto open function, which there doesn't seem to be one, although there is this got focus thing here, which looks like it could be related to the image. So as there is no auto open function, and this is the only function that seems to have a valid string in it, I'd assume that this is the start point, and I'd also guess it has something to do with the document itself. So whenever the user gets a focus on the image or the document or whatever, this will execute. So let's go into edit it. So as you can see, there is a lot of junk data here. So normally it would be quite difficult to go through if you're going through line by line trying to figure out what everything is. Originally I thought these arrays were executable data or something, but that's not actually the case. So what we can do is let's select all of this, copy it, and then open it up in Sublime Text or whichever text editor you want to use, and let's paste it in. So let's search for the got focus. Here we go. So scrolling down, you may notice that there are some lines that don't have this array thing on it. Like here you can see it just seems to be a function call. If we Control F this, you find this is actually a subroutine, and as we scroll down we've got end sub, and so this looks like it's going to carry on execution. So we've got the same thing here, if 3 plus 3 plus this document.application.inches to points, and it will call this, set this variable active document. So from what I can gather, it seems that all the lines with array, open brackets, numbers, and then close brackets are actually junk code. So in Sublime Text, we can go ahead and select the equals array equals, Control F, search for all those strings, and then we want to click find all. And then I believe if we do Control Shift K, it will delete all of the junk data, leaving us with all of this stuff. So it has definitely narrowed down a lot of the code for us, and it looks like this second function called is the main function that we're looking at. So we have this variable set as the active document. We then get the alternative text for the document and store it inside of this function. which is then passed to this UXFAJGQC function here. So if we go down to here, it looks like for each value inside of the array that's passed into it, as you can see there is an array passed as the first argument. It will calculate a few values, convert a string, calculate some more values, use that as a character, and then it will loop round back again once it's split some strings. So what we can go ahead and do now, we know what functions are important. Let's clear this up by removing all of that. And let's select this. Where's the end sub? So end functions here. So I'm going to assume we don't need anything from down here. Delete that. And now we have the two functions here. So let's go ahead and select this, Control F, and then rename this to value changer, just because that's what it seems to do. It changes the values in the array that's passed to it. And this is only called once, but let's call this main. So now let's just do some indentation. So we tab that out. And we're basically just trying to clear this up now. So now we want to tab this out as well. We have this else, exit sub, end if, end sub. Also, notice the shell execute here. This will execute that variable there. This looks like an argument. This looks like an argument as well. Then we have this value, which is also another argument, and then this, which is null. So these are the important values we need to figure out what's going on. But before we can do that, we need to figure out how the values are changed. Let's indent this now. This is a for loop. Indent this. Let's select this. And we want to find all. Now we want to change this to array. And then this value seems to be this JNMQUWWY, which is the alternate text. So let's Control F this, rename it to alternative text. So now stepping into here, we have the final string this looks like. Control F. Let's rename this to final string. And then this is made up of the final string plus this stggh. So this is going to be the split string. So split string. And then the split string is made up of this value here, which is equal to blank, it seems. It seems just this is an empty variable. So let's select that first. Find all, blank. We have the alternative text that is being converted to another value, it seems. And then we have this value here, which seems to be a basic sum. So let's go ahead and just copy this out. And luckily Google is able to give us the answer very quickly. Control V, and the answer is 64. So let us rename this to 64. Find all 64. So now it will call string convert, and it will convert the alternative text to whatever the value 64 corresponds to. So what we can do now is we can copy this out, and we want to go to Google again, and let's search for string convert Visual Basic to see what the integer corresponds to. Let's go into here. So the value 64 converts the string to Unicode. Okay, so whatever is stored inside the alternative text will be converted to Unicode. We then have this sum here. Let's copy that and paste it there. So that is a 0. So let's Control F, find all, convert that to 0. So then for some reason we have blank and character 0 and blank. So I believe this is just empty. So let's rename this to empty. And then finally, the last two things we are interested in is this value here, which is equal to this value. So for each, this is going to be the character in the array. So it will loop through each character in the array argument. So let's rename this to character, and then it will subtract this from it. So let's rename this to character minus val. Let's go ahead and actually see what this value is. And it is 1. So it's character minus 1. So we can go ahead and rename that. Character minus 1 and blank. So it will split this value up, which is the alternative text converted to Unicode, and pass in an empty value. I believe it will just split it into different characters. So if you have the string A, B, C, D, E, F, it will split it like A, B, C, D, E, and F. and then it passes in the character -1 as an argument seemingly. So I would guess this is probably used as a lookup table or a substitution table or something. So let's rename this to subtable, and we've pretty much figured out how this lower function works. So it will take an argument array, and for each value in that array, it will subtract 1 from it and take the value corresponding to the offset inside the subtable, if that makes sense. So what we want to go ahead and do is figure out what the substitution table actually is. And in this case, it's the alternative text. So what we're going to go ahead and do is copy this out and head over to the macro window and type in print here and then Control V it and enter. And we need to go ahead and enable the macros. So because we don't really want it executing, we're doing this all statically. Let's go to the gotFocus function, rename this to gotFocus1, save that. Okay. And let's now close this out, close that out. We want to close it again, head to the desktop, open up this, and we want to enable the macros. And as you can see, it hasn't executed anything, so that's great. Now if we go to view macros, go into edit this. Now let's jump back over to here, make sure we have copied the right thing, Control C. Now if we type in print and then the value, there's a runtime error, interestingly. So it looks like we may need to execute this. So in that case, we can make sure to execute it before the shell execute function. So scroll down, the null, get object, document application, and here's the shell execute. So let's F9 there to put a breakpoint, and we run the macros. Now if we hopefully run the same thing, it should now work. So let's go to the end here, and as you can see, it has now given us this string from the alternative text inside of the active document. Let us now select this. What we can actually do is, if we want to figure out what the Unicode data is, we can just go ahead and call string convert, and then we pass in that, and now we just go ahead and copy this out and then replace this. Now we want a print statement. So now hopefully this should print the converted data. Yep. So what seems to happen is it will just make it a wide string. Nothing really interesting here, just makes it a wide string and uses that as a lookup table. We can go ahead and copy this out. Now we have the actual value we need. So this is the alternative text, Control V there. So now what happens is 13 is passed into this value changer function, and it will get the 12th offset inside of this lookup table as it subtracts 1. So we've got 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So the first character is a P. I'm pretty sure it's going to be PowerShell. So if we look at the second value, it's a 1, but subtracting 1 makes it a 0. So this is equal to the first offset, which is an O, so very likely PowerShell at this point. So we have a good understanding of how this actually works. So in that case, what we can go ahead and do is we can probably draft up a basic Python script to automatically deobfuscate everything for us. So if we go File, and then save this to the desktop as deobfuscate.py. So what we want to do is we want to have a def value change function with the array, and the lookup table is going to be a global variable. So lookup table is equal to, see if we can Control V that, yep. Okay, and we want to just add that there. We might need to sort that out, so just backslash. Shouldn't be any other issues with it. Okay, let's add that there. Okay, so now we have for value in array, value is equal to value minus 1. So now we've subtracted 1 from the value. We just want to go ahead and use that in the lookup table. So if we do string plus equal lookup table and then value, now we need to initialize the string before calling that. So string is equal to that, and now we just print string. So hopefully this will work. So now if we do value change, and we want to go ahead and take this array here. So we do value change, and we're going to want to store this inside of a list. Paste that in. Now cmd cd desktop. I believe I have Python linked to the path. I think I do. Python deobfuscate.py, and it seems there has been an error here. So it doesn't actually give me anything useful, and the reason for this is it takes into consideration there's a space here, so it's not handling it as a wide string that it should be handled by. So instead of using this string with spaces, let's go ahead and copy out the original string here. So let's select all of that, Control C, head back over to here, clear that out, and we want to paste it in. There's an issue with this here, so we need to make sure that there's 2 slashes. And there seems to be another issue down here with that. So let's go ahead and let's add 2 of those. So now there should be 3, yep. And now we want to add it to the left side as well. Okay, hopefully that means it's fixed. No, okay. I'm hoping that doesn't cause any issues. So now let's try again. And now we have the full string, so PowerShell.exe. So now the basic deobfuscate is working. We know it's going to create a PowerShell.exe process. We can confirm this by hovering over this variable here, and as you can see, it's PowerShell.exe. So let's go ahead now and do this on another one. So we've got a longer string here. Copy that out. Now we want to do value change. Put it into that again, Control S, and let's run it. So we've got -nop-exec bypass Windows hidden, and then it seems to have a bit of an issue down here, unless that's the actual string. So let's hover over it. Okay, no, that's the actual string, so there was no issue with our deobfuscator. Then we have one of the final arrays, Control C that, put it into our deobfuscator. Value change, put it in a list again. Now let's run it again, and so it's going to be executing from the system32 folder, it seems. Where is that used? Okay, so we're interested in this one, which is the me.inlineshapes.alternativeText, and then me.inlineshapes.alternativeText as well. So 3 and 2. So we can look at that in a second. We've got that figured out now. Let's figure out what this last array is supposed to be. So we want to Control C that, and put it into our value change. Paste that in, Control C, and run that. So it seems to create a new CLS ID or something, which is quite interesting. And that's about all of the deobfuscation there is. So now let's copy this out, see if we can find it using the same method we used before. So let's print it here, print, and it's a lot of base64 encoded data. So we can just copy this string out, paste that in, go to the very start, print that out, and now scroll up. We want to select all the way down, Control C, head over to CyberChef, paste this in, and from base64, as you can now see, we have decoded the data. It's got a few null bytes, I believe, in it. It's a wide string or something. So we can go to hex quickly to make sure it is null bytes. And yep, it is. So now we can go to find replace. We want to replace the \x00 with nothing. So now we have the full PowerShell script after decoding and deobfuscating it. We've got the malicious URL here. That's probably going to be the rsniff document. I'm surprised there's only one, although they'll probably have more that are created dynamically, although it could just be the one URL in this. But yes, so that brings an end to the deobfuscation of the rsniff macros. We're going to take a different approach when it comes to looking at Zloader, especially because it's a different format and they try and make it a bit more difficult. So the method we take for that one will be quite different to this one, although we still probably will use CyberChef. So hopefully you learned something from the deobfuscation, and perhaps you've now got a few ideas of how you can improve your routine of analyzing these statically. Normally it's usually better to do it dynamically, as you can just put a breakpoint on shell execute. You can view everything from the debugger here, Although if you're interested in potentially making a script using regex and stuff to automatically deobfuscate things, learning to do it statically will help a lot when it comes to that. But yeah, that brings it into the deobfuscation of rsniff, and in the next clip we're going to look at deobfuscating zloader. So let's go ahead and do that now. So with the first macros deobfuscated, let's have a look at another sample that also uses macros and see if we can deobfuscate those as well. So in this video, we're going to be having a look at another macro-infected document, although this time it's an Excel spreadsheet. And this document is actually zloader instead of rsniff. So this is quite an interesting sample based on the fact that it doesn't use the typical macros that we see. For example, the one we saw in the rsniff document, it actually uses a different method of obfuscating macros, and you'll see what I'm talking about when we open it up. So this is going to be more of an automation thing because analyzing these macros is very difficult and time consuming. So we're going to take the automated and behavioral analysis approach. So what we're going to start off by doing is let's open up Process Hacker. And so before you start this, you're going to want to firstly install OLE tools if you haven't already. So pip install OLE tools. So I've already got it installed. So first things first, let's open up the malicious Excel document. Password is infected. And we will see what happens here. Let's suspend trusted installer because it uses up all of the memory. So we have the Excel document spawned, although macros have been disabled. But other than that, it looks like a fairly normal spreadsheet, as normal as it can be. So let's go ahead and view the macros in this document. So view macros, and there doesn't seem to be any. So this is what I was talking about when I said it doesn't use the typical macros that many other malware families use. So, you know, if we scroll around this page, we can't really see anything. There's nothing to see here. It's just all blank. There's no other data here, except for these weird dashes here. But other than that, nothing really interesting. Now, I don't really want to execute these macros at the moment just because I don't know what's executing. There's nothing I can do to stop it. So let's go ahead and minimize this. And what we're going to use is a tool inside of OLE tools called OLE Browse. So on the desktop, we're going to do OLE Browse, select our Excel document, which is here. And this will allow us to browse all of the OLE objects inside of the sample. So we've got summary information, workbook, and document summary information. So let's click that and Hexstream. So here you'll notice that we seem to have names of sheets inside of the document. So sheet 1, this weird string, macro 2, 3, 4, 5, 6, 7, and so on. But when we go over to the Excel document, there is only one sheet. So it seems they're hiding the worksheet somehow, but it's not exactly clear how at this point. So we've got to deal with hidden worksheets. And we also know it is using Excel 4.0 macros. It's not going to be the view macros and then, you know, view auto open. It's going to be in a very different structure, and you'll see once we've figured out how to unhide these hidden worksheets. So that's about it for the document summary information. So let's go back. Okay, back to main menu. Let's go into the summary information, view as a hex stream. Okay, it just says Microsoft Excel. We've got this strange string here. Not sure what it's used for at this point. So let's back out of this. And here we've got workbook. So view the hex stream. And this just really tells us some information. So Microsoft Enhanced Cryptographic Provider. And there seems to be some maybe encrypted code here or something, some encrypted data, or it could just be the hex view of the workbook. Not sure at this point. So let's go ahead and back out of this, back to main menu. And that's pretty much all the information we can get using OLE Browse. So let's click OK. Actually, let's close that out. So quit. So now with the knowledge that they're using hidden worksheets as well as Excel 4.0 macros, we can use a tool called OLE VBA and pass in the Excel document. So let's run that. So it will perform a basic analysis of the file. It will gather information about the different cells that it uses. So notice that we have loads of different cell formulas here. So it tries to parse all these cells. And the reason for that is because Excel 4.0 macros will actually have the instructions inside of these cells. So they can simply have something like call and then a $sign and then whichever cell they want to call. So for example, H1, and when that is executed, actually I forgot to add the equal here. So when that is executed, it will execute H1, which will then have another value, which will execute another value, and so on. So that's what makes it really obfuscated, and there's tools out there to automatically extract all the information from it. But in this case, we're just going to be relying on using OLE tools and a command that will unhide the documents. So back to the command prompt. Let's scroll all the way to the bottom to find a table of everything that's been discovered in the sample. So here we have type autoexec and then keyword auto_open. So this will run when the Excel workbook is opened. So even though it's using Excel 4.0 macros, it still has auto open. We've then got shell execute A, which may run an executable file. We've got shell 32, which again may run an executable file. We've got open, call, URL download to file A, which is really interesting because that's probably going to be used to download the malicious payload. Then we've got hex strings, run dll32.exe, and this byscles.dll. I would guess that that's where the file is downloaded to. So it's not really interesting at this point. We are mainly interested in the auto open, shell execute, and the URL download to file, as well as maybe the call, because apparently it can call a DLL using XL4 macros. We have all this information about this sheet, but we don't have the actual malicious functions. So there is actually a way to show these worksheets without hex editing everything. So there was this great tweet put out by someone that I'll link to in the video description that basically said how you could go about viewing these hidden worksheets without hex editing everything. So if we go ahead and press Alt and F11, it will open up the Visual Basic editor. And if we do Control G, it will bring us the console window. And what we can go ahead and do is paste in this small command that will be for each WS in sheets, and then ws.visible equals true, and then it will loop back around. So this just loops through all of these sheets in the document and sets them to visible. So if we go ahead and hit enter, then we minimize this, we can see that there are now a load of macros inside of the document. So if we go to macro 23, it still seems pretty empty. There's no indication of what is here. There's no text or anything. So let's go ahead and ignore all of these macros here and see if we can find the one with the actual name. So here we go. Here we've got the strange looking strings, and you'll notice there are some lines on the screen, and these are actually instructions. So here we have 161. So these are probably characters or encrypted data that is all appended together and then decrypted. Here we have a run command that will run whatever is stored in the cell T1999. So as you can tell, it's definitely going to be a pain to manually deobfuscate these things by hand. So using the knowledge we have gained from this OLE VBA, we can actually search for these strings to see if we can locate any URLs or anything. So obviously there's no command and control server in plain text in here because otherwise it would pop up. But we do know run DLL32 is used, and it will probably be used to execute the DLL file name here. So byscles.dll. It's probably going to be executed by run DLL32, and I guess it will be downloaded using URL download to file. So we can actually take a similar approach to how we deobfuscated the ursnif macros. So we can actually use Control F to locate run DLL32. So run DLL32.exe. Go to options, and we want to search within the entire workbook because we have a load of different macros here. So it's always helpful to search over all of them, and the rest of the stuff doesn't really matter. We don't need to match case or anything. So let's find all, and it only finds one run DLL32, which is down here. So let's just jump down to that now and zoom in a bit and close that out. So here we have a run command, a call command, and another call command, and then a halt. So halt is basically something that will stop execution, as the name suggests. So if this is executing in a top-down fashion where it will go execute that line, then that line, then that line, it will basically call these two things here and then call halt. So at this point, the downloaded DLL will have run. So let's expand that a bit more. So based on this call alone, we can probably assume it's going to be calling create process and creating a run DLL32.exe process, passing in the argument DLL register server, and this DE1337 is most likely going to be the file name that is downloaded. So we could go ahead and execute this without doing anything, but the problem is it will end up executing this run DLL32 here, and we don't really want to have to deal with any other processes spawning, and we just really want to extract the URL as soon as possible. So if we go ahead and search HTTP now, find all, you can see that there's no existing URL inside of the workbook. So what I'm going to do first is I'm going to put a halt command here. So if it is executing in a top-down fashion, this should halt execution before it executes the DLL. So what we're going to do is let's drag this to the side here and watch the process hacker window to make sure that nothing executes. So if it does, we'll have to restart and maybe put a halt breakpoint replacing this call here. Now if we go options, enable content and run it, we can see that nothing has executed, which is always a good sign. These values seem to have shifted a bit during execution. I don't know if you noticed them flickering about a bit. So it's probably the values changing in the cells, which makes sense, but we are officially halted at this point. So now if we do Control F and search for HTTP again, find all, you'll now notice that it has decrypted the URL and stored it here. So this is the Zloader command and control server. Obviously you can see it's a bit old. This was filmed a while ago, but the audio ended up cutting out, so I had to refilm it. So yeah, I mean, that's pretty much how you can utilize OLE tools and similar tools, so like RTF object dump and any other different malicious document analyzers you can think of in order to help yourself analyze these samples. So by OLE VBA telling us that run DLL32 was in here, we didn't have to find it firstly, and we could instantly jump to it and figure out, okay, it's going to execute a DLL. So if we put a breakpoint before it does that, we probably will be able to get the command and control information as well as the file. But yeah, that pretty much sums up the quick video on Zloader analysis. So as I said, it's going to be really difficult if you were to do this statically and by hand. And there are tools as well that will help you do this, and I'll leave links to them as well. I believe Dissect Malware or Malwareologist has developed a set of tools for dealing with this stuff. So I'll link to those as well because they're very helpful, and they're also written in Python 3, so if you want to learn some Python and figure out how to interact with these Excel documents, I'd highly recommend checking it out. So yeah, that wraps up the macro stuff for this chapter. In the next part, we're going to be looking at equation editor exploits and firstly taking a more technical approach and statically analyzing it, and then we'll take a similar approach using OLE tools to automatically extract IOCs, saving you a lot of time. But yeah, thanks for watching and hopefully you learned something. Let's jump on to the next part. So now we've had a look at the different malware families utilizing malicious macros in their Word documents. Let's have a look at a sample that exploits equation editor in order to download and execute a follow-up payload. Okay, so what we're going to do in this part is we're going to be looking at a malicious Word document that utilizes a equation editor vulnerability. And these are extremely common to find with malware like LokiBot and everything, as the vulnerability is quite persistent on a lot of versions of Microsoft Office, and ASLR and DEP should protect against this, but as equation editor is a very old executable and has been statically compiled, it means that it's useless against preventing the exploits, and so it's one of the prime exploits for attackers to use. I think they've updated that in Windows 10, so it won't work as well. However, we're running from Windows 7 and a lot of people still use Windows 7. So in this case, we should start seeing something. Sometimes you may not realize if a Word document is using malicious macros or exploiting a vulnerability. So in this case, we're going to start off by performing some basic behavioral analysis. So let's go ahead and extract this. Password is infected. And let's rename this to equation. So if we go ahead and run this, keeping an eye on Process Hacker, we can see equation editor has been spawned here. We now have a PowerShell window that pops up and a few other things happen. So we were lucky enough to catch the equation editor process executing. So now we know for sure it is exploiting equation editor. What was also interesting was they've not put as much effort into testing the malicious Word document, as you saw the PowerShell prompt pop up and then loads of red text appear. So that means there was an error in the code. But in this case, we're not really nitpicking over the code. We're just going to be looking at how we can extract this. So let's go ahead and close this out. Now we know it's using equation editor. And we have a few options of what we can use. We can try and use OLE tools, or we can simply go ahead and debug it. So in this case, we're going to be debugging the malicious Word document and following along with the exploit. In the next equation editor analysis, we're going to be using something like OLE tools to see if we can get anything out of the binary. So what we're going to start off with is opening up X32 debug, and we're going to create a Word process. Let's create that. Okay, so what we're going to want to do now we have Word open is we're going to want to attach to it with the debugger, and let's select WinWord. So now we're attached to the Word document. Let's go ahead and run the debugger first so that we can open the file without any breakpoints being hit. So let's open, and we go to desktop and select the equation editor file. Now before we select it and open it, let's put a breakpoint on co-create instance. And the reason for this is equation editor is an out of process COM server, and so Word will utilize COM functions to interact with it. Therefore, putting a breakpoint on co-create instance will allow us to stop the process just before equation editor is created. So once co-create instance is called, we can simply execute the debugger until it hits the return. And at that point, equation editor will have been created, but it won't have any commands passed to it, and therefore we can safely attach our own debugger. So as you can see, it's accidentally hit this breakpoint here. We haven't really done anything. So let's just shift F9, and now we can select our process. So we're going to need to run the debugger again, F9, and open. So now we have technically opened the file, it's just not showing it. So what we're going to do now is we're going to spectate this Process Hacker window until we see equation editor being created. So let's just run the debugger. I'm going to use Shift F9 to do so because that will handle any exceptions. Okay, so we just keep running while monitoring the write window. Okay, and there we go. Equation editor has been created now. So let's go ahead and open up another debugger. Okay, so now we've got X32 debug open. Let's attach to equation editor. So the old vulnerabilities inside of equation editor still occur today, mainly because of the fact that it's statically linked, and DEP and ASLR don't actually affect equation editor, and therefore you can still exploit stuff like buffer overflows and stack overflows. I believe in this case the malware is exploiting a stack overflow. So luckily for us, because it's been statically linked, it will always load at the offset 4 followed by 5 zeros. And so if you look at write-ups that explain where the exploit occurs, you'll be able to see the address that the Stack Overflow occurs, and the offset for that will be the same as in your debugger, if that makes sense. So as an example, let's open up Internet Explorer, and we're just going to go ahead and view this image by Palo Alto, which basically gives us an overview of where the exploit occurs. So as you can see, this is the function where the exploit occurs. It will try and copy data, and it will accidentally copy too much. You'll also see the CMD exe stuff here, so that's definitely a Stack Overflow. So the offset this occurs at is 411658. So now if we go to the debugger, go to equation editor following disassembler and then search for the offset 41165A. Go to it. You can see now we have the move ECX EAX here, and it's the same in the image. So what we can go ahead and do is let's close that out, scroll up to the entry point of this function, and let's put a breakpoint on it. So now we jump back to the Word debugger, remove the breakpoint on co-create instance, and we run it. So now we jump back to the equation editor stuff and we run the debugger. You'll see that it will hit this function here that we've put a breakpoint on. And now if we look at the stack, so the arguments pushed, in this case, we have this address in memory here. Right click, follow dword in dump. You can see that there's some hex data here that looks quite strange. So I believe this is actually supposed to be a font type. So this is the formatting. So it'll give you information on the font because it also compares it later on. So as we step through the process, you'll notice that it has strings relating to font types. So if we go back to this now, if we actually follow this address in the disassembler, you will notice that it's valid code. So we have this value moved into ECX, we then negate it, then we move a few more values, we move this value into EDX, add another value to EDX, and push EBP, then we call ECX. So this looks like it's resolving an address to store into ECX, push it, and then call it. So this is actually the malicious shellcode that is called as a result of exploiting the function. In the image, we saw it was passing cmd.exe, but in this case, it's passing shellcode. So as we step through the function, there's a few more repeating move instructions here. It will call a few functions here, but we're mostly interested in the value when it hits the return. So because it's a stack-based overflow, the return value will probably point to the shellcode. So if we hit the executable return button here and we hit the return, now we check the stack, we have this address in memory, which it will return to first. So we hit the return now. And as you can see, the offset of the shellcode is actually now at the top of the stack. So calling return again will make us return back to the shellcode. So at this point, we're now in the malicious section of the shellcode. So if we view strings, there's really nothing interesting there. But if we step over these few instructions, we call ECX, which is a call to global lock. Now we take a jump to EAX, another jump, we call this function here. Let's go ahead and step into that. Okay, it's just back up here. Step through this, another jump, few more instructions. So this shellcode looks like it's possibly being generated by an exploit builder or something. It's unlikely they'll develop it themselves, especially when it comes to Lokibot. They'll normally just select a payload, it will automatically put it in for them. So as we step down, there's a few more instructions. We're basically looking for an instance where we have API being loaded, and I mean this looks like some sort of API hashing routine, as it will compare EBX to EAX, and in this case they look like two different hash values. So what we want to do is put a breakpoint here on this jump and we run. So now the two values match and we just need to figure out what API was being loaded there. So we step through this and we have this call here. We have this call here again. So this looks like it's querying the process environment block. Okay, we'll push the process name and we'll push kernel 32, step in here. Looks like it's attempting to load the library, see if it can get the offset of kernel 32. Jump back up and now we'll push ntdll. Okay, step in. Doesn't match, so it will return again. Jump back around. Now it has the address of kernel 32, so it will return. And at some point, yeah, you don't want to scroll too much as well because it will end up messing up the flow. So as you can see, we've got move EBX EAX. If we scroll, it will pretty much just reanalyze it for us, which isn't correct. So let's just keep going. Step in here, keep stepping through, see if anything's interesting here. So this looks like it's another API hashing routine. We've got some APIs from the side here. Okay. There's a compare instruction here, so I'm guessing this is probably going to be comparing the hashes. If it doesn't match, it will jump down here, otherwise it will continue, and then it will jump down to here. So we want to put a breakpoint right here. So let's run the debugger. Okay, so it has a breakpoint on load module, which is quite interesting. I didn't realize kernel 32 had a API called load module, but let's keep going down. So the return value will be the address of load library W. step in here, let's hit the return here. Okay, it will now return get process address. So I'm guessing that load module was one before load library. So here the return value is get process address. Now we step into this function. We call get process address on this value here. So now what happens if we step over this? It will return expand environment strings. So now we push EDX, step in here, we call expand environment strings, step in here again, we call EDI load library. Okay, a few more things going on here, and it seems to have crashed immediately. So that's quite annoying when that happens, but we do know sort of where to break for the next time. So we need to put a breakpoint on load library W. So knowing this, we can go ahead and close that debugger out. Now file, we want to basically restart what we were doing now. So if we go to Word, we then want to minimize that, file, attach to Word. We go to breakpoints. We make sure that the co-create instance breakpoint is disabled. So now we simply shift F9 this. We go to File, Open, and Desktop Equation. Now make sure to reset the breakpoint here, and we'll have to run the debugger a few times until we can click Open. Okay, I think at this point we have opened the file, so let's just keep running until we see equation editor being spawned. Okay, so now we have the equation editor process spawned. We can go ahead and open up the other debugger. Luckily, our breakpoint from before is still set, so we automatically break on the vulnerable function entry. So let's remove the breakpoint on that function, and let's simply run the Word debugger, and we run the equation editor debugger. So we hit the vulnerable function. So what we're going to want to do now is put a breakpoint on get procedure address. And the reason for this is because we know it's being executed inside of the malicious shellcode. So we put a breakpoint on there, hit the return, and we take the return and we hit it again. So now we're in the malicious shellcode. Step over that, take the jump again, step into there. And we want to put a breakpoint just about here when it has resolved whatever it's resolving, or decrypted the next layer of shellcode, it seems, not entirely sure. So now let's run, hit the jump, we step into this function, step into there, it's querying the process environment block. This is the comparison for kernel 32. We jump back up here, we actually want to hit the return here. So now I'll return with the pointer to kernel 32, step into here. Somewhere here is probably going to be the library loading function, step into this one. Okay, we call get process address here, get procedure address, I always confuse those two. So now we hit the return. We've loaded expand environment strings. Now we want to step into this function. We call expand environment strings, step in here again. We call load library on URLmon. So this is where the whole retrieval of the PowerShell script seems to come in. So we call load library on URLmon. Okay, hit the return. So now we are seemingly returning everything. Hit the return again. Okay, we want to go back to where we were before. So let's just return a few spaces, put a breakpoint here, just in case execution resumes. Step into here and put a breakpoint there. So sometimes the debugger can mess up when dealing with shellcode, so we just want to make sure that we've got breakpoints on the calls after we return from this. So because we can't just return to user code, because the user code's inside of equation editor and not inside of the shellcode memory, so we can actually remove this breakpoint here. We don't really need it. Okay, so hit return and hopefully hit the return again, hit it again. We're just trying to return back to our shellcode without calling anything else that doesn't need to be called. Hit return again, and here we are. So luckily nothing else called. We weren't stuck in any functions we didn't want to be in. So now we can go ahead and step inside of this function here. So we push EAX and we call get process address on something inside of URLmon. If we step over that, it doesn't seem to have loaded anything. Yep, it couldn't find the API. So we continue on. It pushes this value here, step in there, call EAX, and it seems there's an exception here. So whatever is stored in EAX, I'm guessing was supposed to be the return from the get procedure address. So it looks like the shellcode has messed up here and it hasn't actually created any other processes. So the reason for this is, I think, because we're debugging it again, Word didn't process it or something. So in that case, we're going to have to pretty much close everything and then retry. So I'm just going to skip the bit of just getting back to this point, and I will start recording again when I'm at the call to load library for URLmon. So let's go ahead and jump over to that now. So I'm now at the call to load library. So hopefully it will work this time. Step over that, step into this function, push EAX. I think we might have to go about resetting the machine. Okay, no, so luckily this time it has managed to load the API URL download to file. So now if we step into this function here, we call EAX here, URL download to file, which is interesting because it's not actually pushing anything URL wise to it, it doesn't look like. Let's follow d1 dump. Okay, it doesn't seem to have anything reaching out to a C2 or anything. So if we call that, so it looks like it's reached out to a remote server. Interestingly, I didn't see it push any URLs there or anything, but we can see the path it dropped it to. So if we go to computer, local disk, users, public, we have the downloaded application here. So it's quite interesting how it didn't push a URL anywhere there. But anyway, let's carry on for now. We can go ahead and come back to this and see why we weren't able to find a URL there. So let's step into this function. It calls load library, and then we step into this again. We call get procedure address, sys allocate string, call load library again, get procedure address. We load in RTC shell. Looks like it's possibly using a different method of calling shell execute. So we call RTC shell. What are we passing in? Okay. Nothing really interesting going on here. Let's watch process hacker, make sure it doesn't create any processes here. Step over. Okay, so it does call a process here. So I'm guessing this RTC shell is responsible for executing the 908 file here. If we go ahead and run this, you'll see that it tries to execute some PowerShell and then just decides to exit. So that makes sense why we were getting the pop-ups that were causing it to exit. So now if we step into here, we call get procedure address for exit process, and we call exit process. So that pretty much sums up the equation editor vulnerability. Obviously it's quite a bit in depth in the practical side. If things were a bit confusing, I'd suggest checking out the PDF we provide alongside this, which goes into depth on analyzing this. So what I want to go ahead and do now is I want to go back to that point where it called URL download to file and see if we can locate the URL inside of it. So let's go ahead and give that a try now. Okay, so we're at the point where we call get procedure address. So it's loaded in URLmon download to file. So we see it push 2 zeros here. Then it'll move the address of the file we're going to save it to into EDX, and then we push EDX. So what we're going to do is let's go ahead and view MSDN here. So we want to search for URL download to file W, and this is very zoomed in here, probably because we're looking at that image. So the first argument is the caller, so appointed to the controlling interface of the calling ActiveX component, and the second argument is the URL. Then the third is the file name, so we're interested in the second argument. So let's step into this function here. We push 0. So this seems to be the second argument here. So if we follow d1 dump, we can actually see the URL now. So before that looked like there was a regular return to the previous address. So this here is the location of the URL. So if we follow the selected address and dump, you can see we've got the HTTP stuff. So obviously this can be difficult to recognize as X32 debug decides it's going to be code rather than data. And I mean, there's no way to really stop that unless you're looking at it in IDA. So now we know that, we can go ahead and expand this URL because it's a bit.ly URL, so it's shortened. We can go ahead and expand that, and then yeah, that's pretty much wraps up the analysis of the equation editor vulnerability. So as I said before, if you want to learn more theory about it, we have a additional PDF regarding equation editor and the exploit of it. So you can go check that out. Inside of that PDF, we'll look at, how it's exploited and everything, as well as potentially looking at the shellcode and how the shellcode operates inside of it. So yeah, that wraps up the more technical analysis of this exploit. In the next part, we're going to be analyzing another equation editor exploiter. However, we're going to be taking a less technical approach and a more automated approach, so hopefully being able to extract the shellcode and URLs without even going into a debugger. So yeah, hopefully you learned something from this, and I'll see you in the next part. So we've had a look at the first equation editor exploiting sample. Now let's find any indicators of compromise inside of it. Okay, so now we're going to go ahead and take a less technical approach to extracting the shellcode from the equation editor exploit. So we're going to be using a tool called RTF-dump in this case. We have got OLE tools installed. However, if we just open up a command prompt, cd desktop, if we run RTF object and pass in the equation editor document, you'll see that it tells you that it's not a well-formed OLE object. The main reason for this is because it's highly obfuscated. There's a lot of stuff in here that puts off RTF object. So in that case, let's go ahead and start up RTF dump. So that's RTF dump and then -h. So this will basically show us all the RTF objects inside of the equation editor document. So if we go ahead and do python rtf-dump.py equation.doc and run it, it will give us a long list of different objects inside of the document, and there's so many that it will cut off half of it. So in that case, we need to go ahead and pipe this out to a text document. So let's just say output.txt. So it'll output it to the desktop here. Open up Sublime Text and drag in output.txt into here. So as we scroll down, you can see there's a lot of data here. So we can see the sizes of the objects. So here we've got RTF9 as well as the ID and level of it. So as we scroll down, we can start to see info, author, operator, font, table, and then a few other things that I've never seen in my life. So this is probably to do with the obfuscation. There's a lot of junk data in here. I actually was looking at it earlier, and there's just random Latin phrases randomly put into it. So that's a good example that it's not just macros that can be obfuscated. So as we scroll down, we've got a lot of empty objects here. Then we hit this color scheme mapping, latent styles, LDS locked accept, data store, and at this point it gives us, this is the MS-XML2 SAX XML reader, and it gives us an MD5 hash. This is nothing important really, it's nothing interesting. It's got a file header there, but this isn't the location of our shellcode. So we keep scrolling down. There's a huge amount of stuff here. As you can see, we're already in the thousands. So we now get to info, author, operator. Then we have unknown type 1, 2, 3, 4, 5, 6, 7, 8, 9. So I'm starting to think that potentially this could be the shellcode or something. Although it is quite small, this is the sizing of it. So let's go ahead and check it out, just in case it is something useful. So we want to Control C on the ID. Then we want to do python rtf-dump.py -s, and then we want to paste in the ID number -h to show the hexadecimal, and then we want to pass in the equation.doc. Run that, and it will output the hex edit of the object we're looking at. In this case, it just seems to be a string, nothing really interesting going on here. I can't see how that's going to be shellcode, so let's keep going. So we've got this def PAP thing, mpos, mop, another unknown type here, so let's check this one out, see if it's anything useful. So we erase the 1138 and replace it with 1163, paste that in. Again, doesn't seem to be anything useful here. Scrolling down, we've got this bin object here. Seems to be 0 bytes from what I can see. So let's see if we can view a hex edit of it. So replace that to 74. And it's completely empty, nothing's in there. We've got \b, again that seems to be 1 byte. So let's keep scrolling down. Obviously, you won't normally find the same document twice, so if you looked at another document that exploits equation editor, you probably won't find as many objects as these. This is just the specific obfuscator used. So let's keep going down. Okay, we've got \bin here, so let's go ahead and select that. It seems quite big, so it could be our shellcode or something else. So let's clear that out, and we want to change the 1174 to the ID of \bin, so paste that in and enter. Okay, definitely a lot of data here. Scroll all the way to the top, and as you can see, it doesn't let you view all of it again. So we're going to need to output it again to the desktop. So output to.bin, and we're going to drag that into equation editor. So as I was talking about earlier, we have a lot of Latin just chucked in here, nothing really interesting. Let's keep scrolling down. There's some English as well. And then we start getting to the sort of raw binary data here. So this UTF, I don't think that's an actual string. I think this is possible shellcode at this point because of all the random data, but it doesn't seem too random. So let's keep scrolling down. And automatically I notice the HTTP here. So this is the URL we're looking for. So at this point, we can go ahead and call the analysis quits. We don't need to analyze it anymore. But this is the URL that was reached out to in the process. Here we've got sysalloc string, RTC shell, exit process, the different API. So if you wanted to, you could probably extract this all and then analyze it. I don't believe it's all shellcode. I think a lot of this is junk as well, mainly because the shellcode we analyzed was quite small. And there's a lot of binary data here that is probably nothing more than junk code. Although we have now located the URL, so that's good. Let's just keep scrolling down, and we reach the end of the file. Nothing exceptionally interesting in there, so let's continue on. So we've looked at \bin. Now we've got \object data, which is another fairly large object. So let's go ahead, copy that out, see if we can find anything interesting in this one. So remove the 1661, paste that in, enter. And interestingly, this looks like a copy of the shellcode, although this seems to be a much smaller object than the previous ones. So we've got the bit.ly URL here, sysalloc string and everything. So I think this is the entirety of the shellcode. This is pretty much what we see executed when the stack is overflowed. So you can go ahead and dump this out, knowing this is most likely the full shellcode. So yeah, that pretty much sums up that. Let's keep scrolling down, see if we can find anything here. Anything else interesting? Seems to be empty, although there are two more things we can check out. So we've got this 1682, clear that out. We might need to dump it to a file, but let's paste this in and enter. Okay, scroll up. So we've got some more strings here. This time we've got URL download to file, expand environment strings, and notice at the top here we have the object name, which is very similar to the string equation, and this looks like the actual Stack Overflow code. So I'll delve more into this Stack Overflow inside of the PDF, where we look at the headers and where the return address is and everything. We'll see how the internals of it work. So in this case, we can just pretty much extract this. We've got the IOC where it's going to download the file from. We know where it's going to save the file to, and yeah, that's pretty much about it. We also know how the file is retrieved. So a call to URL download to file. But yeah, that brings an end to the less technical analysis of the equation editor exploit and pretty much a more automated version of it. So you can probably build a Yara rule to detect where the malicious shellcode is. So search for strings like HTTP and everything, and it should narrow it down. They've provided a RTF Yara rule here. You can dump out all of these objects and then run your own rule against it to see if you can locate the URL. But yeah, as I was saying, that brings an end to the equation editor analysis. So the automated one and the more hands-on approach. So yeah, let's head on back to the presentation. So to recap, we've had a look at malicious Word documents and both pathways they commonly take. So we've reverse engineered 2 documents containing malicious macros, as well as reverse engineering 2 documents containing equation editor exploits and gathering IOCs from those. In the next part of this chapter, we're going to be looking at the second stage loaders. So we're actually going to be reverse engineering compiled malware, so what is downloaded by the malicious Word documents. So yeah, that brings an end to this part of the chapter. Hopefully you learned something from it, and let's jump into the next one.